Dr. Branch started off in South Africa where he got his bachelor's and master's, and then he jumped several ponds over, or jumped two ponds, and got his PhD at the University of Wisconsin. Oops.
Washington.
I did it. I know it was in good. Sorry, I'm from the University of Wisconsin. University of Washington.
The other UW.
The other UW. The illustrious School of Aquatic and Fisheries Science. Now, Dr. Branch has numerous awards and has published more than 60 peer-reviewed articles, and that includes articles in both Science and Nature. As many of you heard last night, what Dr. Branch specializes in is taking the dominant theories that governs what we think we know and the way we view marine fisheries and food webs, confronting them with large data sets and sophisticated models, and re-educating us. Or I hope re-educating us. And he's been a part of a paradigm shift that has changed the way we, and hopefully the public, view marine fisheries. And tonight he's going to be sharing his research on how fisheries affect food webs. And please join me in welcoming
Thanks, Jeremy, and thanks to all of you for coming. I hope I can live up to that introduction, but we'll see. Today's talk, I'm going to talk about how fisheries affect food webs, and I'm going to go over a few things. So here's a structure for the talk. I don't often have a structure to my talks. I just sort of go on. But I'm going to go look at the early history of how we think about food webs, look at a dominant paradigm, which is fishing down marine food webs, look at how people have taken that concept and become increasingly impassioned about it, and then think about, well, are there other hypotheses out there that might also explain some systems? And one of them is, of course, work that I've done, trophic fingerprint. Look at a few sensitivities to that, and then, of course, as is my wont, I have to close with a limerick. So I'll leave you waiting for my limerick. Okay? So some early history. The concept of food webs and trophic levels actually dates back, way back to the early start of the 20th century. So Elton, 1927, and Lindemann, 1942, were the first guys that really thought about this in any systematic way. So Elton's idea was that there are these trophic levels. There are carnivores and herbivores and so on. And Lindemann said, well, let's quantify this and make them integers. Let's define plant matter primary productivity as integer level 1, herbivores integer level 2, carnivores integer level 3. So these were the early pioneers in this system. The next step was to say, well, you know, it doesn't actually make a lot of sense to say that a predator is at exactly trophic level 3. And what happens if they eat, you know, some berries and they eat some fish? Now, they can't be at an integer level in their position in the food web because they're feeding partly on plant matter and partly on things at a higher trophic level. So doesn't it make sense to think about an integer trophic level? So for example, if you feed 40% on plants and 60% on herbivores, then your fractional trophic level is somewhere between 2 and 3. And that's the equation you'd use to get to 2.6. So integer trophic levels, let's move on and look at fractional trophic levels. So my question for you is, where do humans fit in food webs? What is our average trophic level? Anybody like to guess? People in this room?
What about wing?
Are there some Argentines here? No, they're way up. In general, if we were to take the world's population as a whole, on average, where do humans fit?
2.3.
Someone read the paper. 2.21. Because most of what we eat is plant matter. Very little of what we eat is meat. And in fact, the highest trophic level that we would be as humans is if we eat seafood and other fish species, because many fish occur at trophic levels 3, 4, or even higher. And if you eat tuna, That's above trophic level 4, which makes you trophic level 5 point something. Now, building on from this work, Regier was the first person that said, you know, as we fish systems, he was looking at the Great Lakes, and he said, you know, as we fish systems, it's interesting that we seem to go from big things to small things, from more valuable things to less valuable things. And he looked at a whole sequence going from lake trout, sturgeon, whitefish, herring, catfishes, and walleyes, and yellow-eye perch, and smelt, and showed that there's actually a very predictable sequence of development of fisheries and then a reduction in their catches. And he suggested this was driving the Lake Erie system from large and long-lived bottom-dwelling forms, benthic forms, to small and short-lived pelagic forms. So working off from that, Jiming actually was the first person to say, you know, we can look at catches that are taken from all different trophic levels and get a mean trophic level of all catches, so weighted by the amount of catch taken at each trophic level. So if you were to go and look at every fish species caught, assign a trophic level to each one of those, get the catches for each one of those fishes, and take a weighted average, weighted by the catch, you would have, just like we got for humans, you would have the average trophic level of the catches. He did it for the North Sea, 1982, and showed basically no change. You know, mean trophic level range, 3.62, 3.76, you know, almost no change. Guess how many citations he got? 5. All right, 5 citations. Okay. So that's the background. And then we get into this concept of fishing down marine food webs. The first person to coin this term was Willy Christensen, 1996. He works at the University of British Columbia. And he said, you know, as we look to systems that have higher trophic levels on average, we tend to get fewer catches from them. So that's the plot you can see over here, that if the system on average has a low trophic level, you'll get a higher catch per kilometer squared. And he said, you know, in unfished areas, we could expect there to be some kind of balance, often with high abundances of predatory fish. And initially, we will think about humans targeting large, predatory, and often higher-priced species. And as the fishing pressure takes toll, those species will decline, and we'll end up fishing on smaller and smaller species. This paper did pretty well, but the real blockbuster was the paper by Pauly and Christensen and others in 1998 of the name Fishing Down Marine Food Webs, where they took the concept of mean trophic level and married it with global catch data and global estimates of trophic levels for every species caught by humans. And they got this pattern at a global level. And the key finding here was that globally, the trophic levels of marine catches or landings appear to have declined in recent decades at a rate of about 0.1 per decade. And I'll just point out one thing about this, which is that's what they mean by 0.1 per decade. It's just the last few decades that actually the decline over time was 0.04 per decade. So a bit slower because of that bump in the middle, which was incidentally due to the collapse and recovery of anchoveta. Sorry, the increase and collapse of Peruvian anchoveta at a low trophic level. Okay, so this gives us our dominant paradigm, fishing down marine food webs. And this is the dominant illustration. We started off fishing at high trophic level, top predators, fished them out, got further and further down the food web until, as they put it, we'll be left with nothing but a diet of jellyfish and plankton stew. All right? Haven't quite got there yet, but I have been served jellyfish before. It is out there. Or, to make it a little more concrete, that's what the future holds. Or, if you want to get a little more impassioned about it, you know, we've checked everything out, and fishing down the food web is far more pervasive than we thought. Or maybe we should be counting the very last fish. Or, in fact, maybe it's simply a quackalops now. Okay? Not to say that this is doom and gloom. Maybe it is. But what happened was, over time, this concept really took hold, and people started publishing papers saying, hey, I've looked at my system, and it shows fishing down the food web. I've looked at my system, it also shows fishing down the food web. But some of these papers are a little more, shall we say, dodgy than others. So here's one looking at fishing down marine food webs in India. And you can see the top left panel over there shows you the amount of catch at different trophic levels. So this top little black line there is tunas and bullfishes, catches going up over time. These are the fish at the next level, and those catches are going up over time. These are fish at the next level, and those catches are going up over time. And here are fish at the bottom, and those catches are going up over time. Okay? So, if you were to analyze this and say, are we fishing down marine food webs? I would say no, because catches are going up no matter what trophic level you're looking at. But if you go through that and you first remove the tuna and bullfish, that doesn't make too much of a difference. What about if you remove everything below 3.25 and just look at the top predators? That doesn't really make a difference. What if you just pick a period when it's declining and you say it's declining? And I'm not joking, that's what this paper is all about. So here are the data here showing going up, coming down. They just said this is the period when there was a decline, and that is fishing down the food web. Over here, well, it's this like this, it's this, that's still fishing down the food web. Okay? And if there's a red line to guide your eye showing there's actually no change in mean trophic level over time. So the problem is, papers started coming out saying everything is fishing down the food web no matter what the data actually showed. And I'll give you one more example. This is a paper for Brazil, and what you can see here is just mean trophic level for all species. As you can see, it is not going down, it is going up. If you take out the tuna and bullfish, it's going up, but not as much. If you take out everything except northeast Brazil, it's flat. If you take out everything except northeast Brazil and you take out the tuna and bullfish, maybe it's declining a little bit. All right? And what this paper did was they went even further and they said, let's just take the one little part of northeast Brazil where it is declining, and we'll put that into the abstract. All right? And so the conclusion of the paper was there is fishing down marine food webs. It's happening at 0.16 units per decade, one of the highest rates ever documented. Like almost no relation to the actual data presented in the paper. And there again is your horizontal line. So, my problem with this is you take a paper, you take an area, you calculate mean trophic level, and you ask, is it declining? And if it is, you publish. Right? If it isn't, you go, well, it's got to be that because we're doing it everywhere. So how about if we exclude tuna and bullfish? Is it declining now? Yes, publish. No, oh. What about if we just exclude some areas? Is it declining now? Publish. No, oh, I don't know what to do now. So my problem is, if your dominant paradigm is only looking at one method, one option, one hypothesis, you're going to try and find it. And you will find it. Instead, we should be looking at multiple possible hypotheses for how we're affecting marine food webs and choosing between them. And there's actually this brilliant paper, which I came across, called The Method of Multiple Working Hypotheses, okay, by Chamberlain, originally published in 1890, reprinted 1965. It talks about this problem, where if you come up with a theory that might or might not be right, but you think, this is my theory. It's the problem of parental affection, okay? And he says, with the method of multiple working hypotheses, the dangers of parental affection for a favorite theory can be circumvented. So he says, the process goes like this. The moment one is offered an original explanation for a phenomenon that seems satisfactory, that moment affection for one's intellectual child springs into existence, the mind lingers with pleasure upon the facts that fall happily into the embrace of the theory, and feels a natural coldness towards those that seem refractory. And eventually, the search for facts, the observation of phenomena, and their interpretation are all dominated by affection for the favored theory until it appears to its author or its advocate to have been overwhelmingly established. The theory then rises rapidly to the ruling position. And I would say this is what has happened with fishing down marine food webs. Instead, what Chamberlain says is you need the method of multiple working hypotheses. You need to say, first of all, what are all the possible ways we could be affecting food webs? Then let's go and collect some data and ask, well, what evidence is there for all of these working hypotheses? And once you've done that, then you can decide, well, for my system, this hypothesis can be discarded and this one can be kept. In other words, we need to balance all available evidence fairly and to accept that interpretation to which the weight of evidence inclines, not that which simply fits our working hypothesis or our dominant theory. So I'm going to present some alternative hypotheses here. For example, what reasons could there be for declining trophic level in a fishery? It's not just that predators declined. It could be that the predator was declining in blue and the prey is stable. So that's fishing down food webs, right? Predator declines, the prey stays the same. It could just be the predator's increasing and the prey is increasing even faster. Right? So on average, the catch is at a lower trophic level because there's more prey proportionately. It could be your predator's got absolutely no change at all, but the prey is increasing. Or it could be that the predator is declining even faster than the prey is declining. So there are all these possible explanations just for declines in mean trophic level. And you can flip these all around and say the alternative hypotheses could fit if trophic level is going up. Right? There's still lots of different ways of getting that. So here's one alternative, fishing through marine food webs. And this is by my colleague at the University of Washington, Tim Essington. And he said, it's really odd because when I look at global catches, the catches of predators have not declined. Mostly they've continued to go up or stabilized. So he said, I'm going to go and contrast fishing down where predators are depleted with fishing through where predators are either constant or increasing, but the catches of their prey are increasing even faster. So that would cause mean trophic level to go down. Or the way to think about it over here is the red dots, the red bit here is predators, and they disappear over here, which means they were all fished out, and you're just left with catches of their prey. So that's fishing down. And over here, the catches of the predator are still high, but over time we add catches of the prey, and so that causes a decline in mean trophic level. And he found that out of 30 ecosystems which showed declining mean trophic level, only 9 of those had evidence for fishing down, and 21 had evidence for fishing through. Okay, so this is the kind of evidence-based testing that we need more of. Alternatively, we might be fishing not for predators or for prey, but for profits. I mean, maybe that's not so novel that economics has something to do with it. I can see any economists here? No one's grinning very broadly. One person at the back, maybe one economist. Why do we go fishing? To make money, right? What do we go fishing for first? High-valued things that we can catch easily and cheaply. So Suresh Sethi and myself and Reg Watson went and looked at this, and we got a database of trophic levels and a database of prices, and we said, well, if it's fishing down, then the prices of high trophic level things should be higher, predators should be more valuable, and if it's not, then, well, what factors explain when fisheries developed. And this was total surprise to us. This is the relationship between trophic level and the price, where each dot represents one fish species. And there is no relationship between trophic level and price. Now I can see people going, huh? That's crazy. Okay, how about this? What trophic level is abalone? 2. Is abalone valuable? What about shrimp, crab, lobster? They're not that high. What about sharks? How much do you pay for a shark? Nothing. How much do you pay for a can of tuna? Not very much, okay? It's not as clear-cut as you think. We're used to thinking about, I'm going to go fish, say, in a lake, make it freshwater for you, and catch the biggest fish I can, and that's certainly true. But when you go commercially fishing, you might make more money by catching abalone or oysters or scallops than you would by catching something that's big and high trophic level. So that was, to us, complete surprise. And he only looked at this because he thought, I'd better do this before I do the other analysis to make sure it holds, and it didn't. So what then does influence when we fish on different types of species? The answer is, and here I have to explain a little bit, the x-axis here is development year. So if we look at a time series of catches and we pick the year in which catches first hit 25% of the maximum catch, and we call that the year the fishery was developed or started developing. So it's a metric of when we started targeting a particular fishery. And we regress those data against other factors. We find no relationship between when a fishery developed and trophic level. So if fishing down was happening, we would expect to see high trophic level things fished earlier and low trophic level things fished later, and there's just no relationship. We find that length, there was no relationship either, although this dot here, meaning things developed before 1950, is a bit higher than things developed after 1950. So there's some indication that very early developing fisheries were a little bigger than late developing fisheries. We find that the deeper something is, the later the fishery developed. And that makes sense from economics. Something is deeper, it's further offshore, it's harder to catch, it's more expensive to catch, the cost is higher to catch it. So economic issues. But the two things that made the most impact were price. The higher the price for something, the earlier the fishery developed. So price was a factor. And how big the fishery was. So big fisheries developed earlier than small fisheries. And over time, the size of the fisheries that we developed have gotten smaller and smaller and smaller. New fisheries are now much smaller than old fisheries in terms of their possible production. And if you multiply catch by price, you get revenue, and that shows a very strong relationship. Things that give you big amounts of revenue, you develop earlier. So we have the solution. Things with high catches that are highly valued, that are in shallow waters, we develop earlier. I mean, it's just basic economics, right? But there's another implication of this, which is that as time progressed, even though we've been adding new fisheries every year to the mix, so this plot over here shows the number of new fisheries over time, and I put these in gray because you can't really get an accurate estimate in the last 5 years of whether they were developed or not. Pretty much constant over time. And the cumulative catch we get from these fisheries has increased over time. But these new fisheries produce very little volume to add to global catches. So the cumulative addition of catch to all of global catch pretty much peaked in 1980. After 1980, the fisheries we developed were all very small, very low volume tiny fisheries that haven't added much to either volume or price for global fisheries. In other words, we've reached the limits of what we can catch. We're not going to fish more fish out of the oceans. So there's the value one. The previous one was the volume one. And you can see that adding value to global fisheries has pretty much reached an end. Okay, so what is the status of fisheries? And what do we find when we look at updated data past 1998? So we'll first say that I got into this because I was compiling trawl surveys, long-term surveys of how much biomass there is for a bunch of different species in 29 different ecosystems. And as I got data for each ecosystem, I was calculating mean trophic level for the ecosystem, not from catches. So this is what's happening in reality on the ground. And as I started compiling this, I noticed that I wasn't getting big declines in mean trophic level over time. Some of them were, some were going down, some were going up, some were stable, but there was no clear pattern. And so as I started writing up these results, I thought, well, I should go and update the values from Pawley 1998, the mean trophic level from catch, so I can have something to compare that with. And what I should add to that is all of the stock assessments we'd compiled in the RAM legacy database that I talked about yesterday. So then we'll have research surveys, catches, stock assessments, and I thought, you know, it would be remiss of me to not have models. So I compiled a whole series of EcoPath with EcoSim models. Actually, it was Beth Fulton that did that work. And I should say this work was with a whole bunch of other fabulous scientists. And this is what the first results showed. So I first said, okay, here's the original result from Pawley et al. 1998. There's the decline in recent mean trophic level, the rate of 0.1 per decade. Let's get the new data and extend this time series a bit more. Nothing like the original results. All right? What had happened was that over the last 2.5 decades, mean trophic level from global catch has been increasing. Not only that, but the line was substantially different to the original line in his paper. And it turns out that you can figure out what changed. I wouldn't say what went wrong, what changed, because just estimates of trophic levels for some key fish species were updated and revised. That's the only thing that changed. Okay? So the premise for Fish and Down Marine Food Webs was mean trophic level is declining in global catch. But it's not. It's going up. So that was the first thing that I thought, well, that is weird. And there's the explanation. If you go and replace the current trophic levels in the global database with the ones that were there in 1997, you can pretty much perfectly replicate the results from the 1998 study. That's the red line. What it also shows you is that 1998 was the perfect year to publish the paper before it started going up again. Sometimes you get lucky. But what do I find? I call this the trophic fingerprint of marine fisheries. It's my diagnostic. Right? If there's fishing down, you will see the catches of things at top trophic levels declining in recent years. And as you go further down the food web, you'll see other species catches declining in turn. And what you see instead is, with very few exceptions, catches up at the top trophic level have been going up. And been going up, the exception is the one containing Atlantic cod. Squid, pretty much the same. These squid going up, blue whiting going up, common squids going up, squid going up, redfish going up, scads going up. In fact, as you go through, with very few exceptions, the catches at almost every trophic level group are going up over time. And the labels here are just the single species or group that's most dominant within that particular trophic level bin. So in other words, it's not the case that there's fishing down marine food webs at a global level. Because if there was, we would expect the catches to be declining of the top predators, and they're not. What we see instead is the catches are increasing throughout trophic levels. And I'm not saying that's good. That's pretty bad, right? I mean, I've already showed you in the previous slide, we've reached the limits of what we can take out, and if we've reached the limits, we're not going to be able to get any more out of any of these other trophic levels. Well, what about the models? What do the models show us? The models show us some interesting patterns. The first is, if we simulate fishing down in the model, in the ecopath model, we can generate declines in mean trophic levels. What's interesting is that when you look at mean trophic level in the ecosystem, what's actually happening down the ground, that starts going down and then it goes back up to about where it was before. So how is that possible? If you're fishing down, how can you end up with a mean trophic level that's the same as it was when you started? The answer is you fish down the predators, you fish down their prey, you fish down their prey, you fish down their prey, and now everything is at low levels in about the same proportions as they were before you started fishing. And so the mean trophic level is about the same as it was before. Okay? If you simulate fishing through the food web, you can get exactly the same pattern in mean trophic level in the catches and a similar pattern in ecosystems. If you're fishing for profits, you can still get a decline in mean trophic level in the catches, but you might not get any change in the ecosystem. And if you're fishing everything simultaneously, basically mean trophic level doesn't change. But now look at the bottom panel. That's the fraction of all those species that ended up collapsed in the ecosystem models. You can get just as many or more collapses under this scenario where there's no change in mean trophic level as you do under these three scenarios where there is a change in mean trophic level. So our indicator of mean trophic level isn't very sensitive to what we really want to measure, which is collapses or ecosystem health. Okay, more data, right? Each of these squares represents one ecosystem where I collected data for catches, stock assessments, and trawl surveys. And what you see is it's like a Facebook profile update. It's complicated, right? You know, very often there are negative correlations between the trends in mean trophic level from catch and the trends in mean trophic level from assessments or from surveys. Now, it's maybe good about 40% of the time. So here's an example. Gulf of Alaska, very little change in the mean trophic level of catch. That's the black dots down here. But in a small mesh survey, it shows the ecosystem shifted almost a full trophic level upwards. So this is the fabled regime shift in the Gulf of Alaska, where they have this beautiful shrimp survey where they were using to catch shrimp. And by the end of the time series, you can see over here, the blue has almost vanished, and the shrimp survey has turned into a big fish survey. They're only catching big fish. So that's a case of fishing up. So how about if we summarize all these results from the three different sources? So we have our mean trophic level of catch down here. And each of these little faint red lines is the mean trophic level you'd get if you excluded one of the big dominant species from that time series. The blue lines are mean trophic level from fisheries stock assessments. And the green line is the mean trophic level from all the scientific trawl surveys that I compiled. You know, and these just don't really show any particular pattern going up or down. You could say maybe in recent decades, these have gone up, and maybe these have gone up a bit, and these have stayed the same or gone up since then. It depends what time period you pick, but no clear signal. What about if you just restrict the data to catches and biomass from the same set of stocks? Even there, you can get a case where, over time, mean trophic level in catches is going up, but the mean trophic level from the biomass data is going down. They're negatively correlated. So relying on catch data to get a picture of what's happening in the ecosystem is maybe a little unreliable. Okay, so how about some sensitivities and responses to the data I've shown you? Now, you'll recall that part of what I did was get this mean trophic level in catches from all areas. That's all global catch data. And here's the line from Pauly et al. 1998. If you take out anchoveta and sardine, those big dips and peaks disappear because the dip and recovery is the development and collapse of anchoveta, and the second one is the development and collapse of South American sardine. Because both those are low trophic level species, you get more of them, mean trophic level is going to go down. As they collapse, it's going to go back up again. So much of the pattern is explained by that. If you start excluding the small pelagic species and you only look at 3.0 and above, you get that line. 3.25 and above, you get that line. 3.5 and above, you get that line. All right? So I did all these sensitivities in the original paper. I think you can guess which of these lines was picked as a criticism of my paper. Anyone guess? Yep, that one. Okay? So the first response came out and they said, Pauly said, look, if you pick that line, it shows that fishing down also occurs as an unexplained phenomenon in Figure 2 of Branch et al., a paper supposed to show that fishing down does not exist. I thought, well, that is a good point. But what he didn't know was that I had been contacted by someone saying, I don't understand why you put Atlantic cod at trophic level 4.42 instead of 3.73. And I'm like, what? Huh? What are you talking about? And he said, well, in fish base, Atlantic cod is at 3.73, not 4.42. And I said, no, it's not. I took the value out in 2010, and it was 4.42. And he said, no, it's 3.73. Look, they changed the value. Well, guess what happens to this line when you put in 3.73? Okay, so I published this response. I said, well, that's very interesting, but the data have changed again, and this is what it looks like now. And there was a big to and fro, and the value got changed back to 4.42. So then we had a bit of an argument, and we agreed that actually the way you're weighting different estimates, so there were basically 7 estimates of trophic level. One was 4.42, the ones in between, the lowest one was about 3.5. And if you weight them one way, you get 3.73. And we said, well, let's weight it a different way, and you get 4.0 something, and which is what it is now. And if you put that in, so, okay. So that's the problem with cherry picking one line. All right, so I've shown you some stuff. Here are some conclusions. Basically, trends in catches may not reflect trends in ecosystems. And that's clear when you compare catches to trawl surveys, when you compare catches to stock assessments. That what we need to do when you look at your particular ecosystem is say, could it be fishing down? Could it be fishing up? Could it be fishing through? Could it be just fishing everywhere, where you're balanced harvesting or balanced over-harvesting? All of those occur in some places. I'm not saying that fishing down doesn't occur. It very definitely does occur in some places, particularly the Northwest Atlantic. That fishing down does imply a declining mean trophic level, but a declining mean trophic level doesn't imply fishing down. It could be fishing through. And finally, if you really want a big explanation of what's happening, it's profits, right? We're going to target high value, abundant, easy to catch species first. we'll always target and access those first, and we'll always deplete those first too. So, I know you've been waiting for it. Here's my limerick. Right? Are we fishing from sharks down to krill just to put some nice fish on a grill? Got some data to check, and I found, what the heck? Fishing for profits, not jellies. So chill. So I wanted to thank a bunch of co-authors, and I'll leave that up there and leave time for questions. Yep.
You showed how sensitive it was to the mean trophic level. Is it possible that the mean trophic level of the fish could actually be changing?
That's a very good question. And one of the shortcomings of doing this kind of study is we assume that there's the same fixed trophic level for every species, not just over time, over areas, and over ages. Okay? And it's certainly true that as we fish species, the average age goes down and their place in the food web goes down too. Now, some analyses have been done looking at that, and they suggest that the change in composition of species is much more important than any change in trophic level over age or area or time. But it certainly is a factor it would be nice to get at. Unfortunately, with more than 1,000 species, there aren't area-specific estimates, age-specific estimates, and time-specific estimates. Yeah?
She stole my question.
Oh, okay. That's easy. Yep.
So something that you hear a lot about but often don't see much data on is the relative increase in the number of jellies everywhere in returning to the ocean. You looked at that in this kind of context?
I haven't, and I believe that there is another debate going on there where one group of people say we'll basically be eating jellyfish sandwiches. And there tend to be the people that work on global fisheries data, but not necessarily are jellyfish specialists. And then another group of people, which are jellyfish specialists, say, you know, jellyfish fluctuate up and down. Right now, they're no higher or no lower than they've been before. So I don't know. I'm not an expert. You know, it depends if you trust the people looking at global data and have experience piecing that together, or the people that are jellyfish experts, but maybe not, you know, experts at piecing global data together. Certainly some areas, yes. Namibia is one. The Black Sea had a big jellyfish infestation that I think is gone now, but certainly some areas do. Yeah?
We've known for a long time that catch isn't really very reflective of the real population there. And so catch per unit effort has often been used. So I was surprised that none of your analyses would utilize catch per unit effort as a metric of the population strength of the species.
Yeah.
Why is that?
I just didn't have the time to compile a database of catch per unit effort. And also there are issues with catch per unit effort in that big analyses that have been done comparing catch per unit effort to trawl survey abundance data suggest that catch per unit effort declines much more slowly than the actual biomass declines on average. And that's true on average, but there are also populations where catch per unit effort declines very quickly and then stabilizes much more quickly than biomass does. So a lot depends on how the fishery is distributed. So, for example, catch per unit effort can drop very quickly if there's a fish that's distributed across a very broad area and a few spots in that area are very high density. So the fishery is going to target those high density places first, get high catch rates, deplete them down, and then the catch rates are going to plummet. But actually, most of the biomass is diffuse and spread over a big area. And so the tuna people I speak to suggest that's what happened to tuna catch per unit effort. So if you just look at catch per unit effort, catch per hooks, it suggests a 90% decline within 15 years. But if you look at the catch data or the biomass data, well, the catches went up fivefold after that decline. So it doesn't make sense. You know, you couldn't have declined 90% and then supported a fivefold increase in catches with a stable catch per unit effort. So, yeah, there certainly are problems, but it's better than nothing. Yeah?
Could you
address a bunch of the recent work that's showing that, or claiming that most of the top predators in the ocean are declining, and I think some estimates put it at over 90% gone already, and how that fits into some of the analysis you've done?
Actually, that was exactly what I was just talking about. So are you talking about, there was a paper by Myers and Worm in 2003 that said 90% of top predators are gone?
I'm not thinking of any specific paper. It just seems like there's been several news
Yeah.
reports and general media reports of that
Yeah.
kind of stuff as well.
Yeah, the key one, I might even have slides. I can't remember what I put at the end of my talk. No, not there. Okay. Sorry. So the original paper that came out was a paper suggesting that 90% of the world's top predators have gone in the oceans. And all of the people that work on tuna and billfish and open ocean species say that this is totally wrong. And the most recent analysis by, it was in PNAS, One Water, they showed that tuna and other top predators have actually declined about 60%. I mean, it's still a lot, but 60% decline is roughly where you would get maximum sustainable yield. 90% decline is collapsed. So if you also look at the catches of top predators over time, we're catching more top predators now than we ever have, and it's been increasing in the 10 years since that paper was published. So to me, it doesn't seem to mesh. Now, sharks have certainly gone down a lot in a lot of areas, sometimes as much as 99%. So maybe if you look at everything, it might be true, but certainly not the commercially caught species. Yep.
What's your impression in the UBC or wherever the groups you work with, of how much people have embraced the idea of using multiple working hypotheses?
I don't think they have. Which is kind of why I want to bring this up and say, you know, if you work in a system, think about all the possible explanations first, and then winnow them down based on data, rather than just going in and saying, there's only one explanation, I'm going to prove it's right. And actually, there was a paper by Ciclurus or Sturgio, where they look at fishing down the food web, and they say, we know it's ecological truth. It doesn't matter how you fish, it's always going to be fishing down the food web. That's just always true. There's actually no need to test it, because it's just always true. I mean, I'd like to think we can test things, but maybe I'm old-fashioned. More questions? Yep.
So, one thing you talked about yesterday was how China does have the power to lay the hammer down, make a decision. If you had that united wand, how would the management change? How would you like to see management of these fisheries change?
Okay, there are two problems here. Okay, the one problem is easy. Let's look at all the big fisheries of the world that are managed by countries with capacity to enforce regulations. I would just say, if it's overfished, cut the catches, rebuild the fishery, and you'll be fine. And that is what we're doing in the States, and what they're just catching on to in Europe, all right? But then there's the other half, which is, what do you do with all the developing country fisheries where maximizing catches isn't the aim? The aim is employment, food security, stopping people starving, giving people a bit of money, and, you know, if they catch 3 fish or 6 fish a day, as long as they have something to eat, that's fine. And you can't control 10,000 people going out in small boats or canoes and fishing on reefs. And there, I don't know. I don't know. I mean, maybe if I had, 10,000 people to go in and go to every community and stay there for 5 years and try to, change the way they think and build some norms for fishery sustainability, and say, well, maybe you shouldn't, fish with destructive gear. Maybe you should set some areas aside where there's no fishing. Maybe that's the way to do it. I don't think you can't just say, stop fishing because people will starve. I mean, you could, and I guess that's what happened in some of China's past in the 60s. You know, that change our agricultural practices and people starved. But, you know, we don't want to do that. So I think most of it is sort of co-management and social change, and basically anthropologists going in and chatting to people, and not so much of this top-down change. That makes sense?
All right, well, join me.
Thank you.